Hello everyone, this is Puya. In this video, I want to talk about basics of linear algebra using MATLAB. Let's do a very basic review of how we can represent vectors and matrices in MATLAB. So a vector is an array of numbers um, or any other item, like can be characters as well, an array of items called elements arranged in a row or in a column format. So um, in order to represent a vector in MATLAB, this is how we can represent a row vector. So you can see that we put a space. We can use space as a delimiter between the numbers, or you can use comma to separate numbers or items in a row. So this is it can be thought as a matrix with one row and four columns, or a vector or a row vector with four items. If you want to represent a column vector, we just use the semicolon. So like a semicolon represent the end of a row. So basically here, like we have only one item in the first row, which is 1, then minus 4 below that, 3 below that, 5 below that. So this is a row vector, this is a column vector. You are all familiar with the concept of transposition, matrix transposition. So if you see this here, if we transpose A, we get B. If we transpose B, we get A. So basically, transposition of a matrix is when you transpose a matrix, you basically replace its rows with columns. So and we're gonna see more about transposition later in MATLAB. If we have all real numbers, you can use a single quote to transpose a matrix, and we will see that if we have complex numbers, it's going to be a little bit different. Like here, because we have all real numbers, we can just use the single quote for transposition. Matrix is an array in a rectangular scheme of items called elements, arranged so that we can have like any number of rows and any number of columns. So here, like, let's assume that we have m rows and n columns. This is a matrix. You see that in the first row we have two items, 1 and 2. So basically this shows that this matrix has two columns. And then on the second row we have again -3 and -4 as the elements. You always have to remember that in a matrix, all rows have to have the same number of columns. You can't have the first row having two columns and the second row having any other number of columns. So in this case, m is number of rows, it's equal to 2. N is the number of columns, it's also equal to 2. If you want to have access to elements of a matrix in MATLAB, you need to provide the index of the row and the index of the column of that element in the matrix. Remember that in MATLAB, indices start from 1, unlike C++ or other languages that the index starts from 0. So in MATLAB, indexes start from 1. So for example, if I want to extract number -3 from this matrix, this number is in the second row and the first column. So I have to write A with round brackets or parentheses 2, 1. First the index for the row, then the index for the column. If I want to access number 2, this is in the first row and the second column, so I have to write A round brackets 1, which is the index for the row, comma 2, which is the index for the column. You can also use the colon operator. So if I use this, they would basically tell MATLAB that I want to have the first row and all the columns in the first row. So basically this would give me the first row. If I do this for this matrix A1 and colon, it would give me all the numbers in the first row. Similarly, if I put the colon in the first place, then it means that I want to have all the numbers in the first column. So this is going to give us the first column of A. So you see that the first column is 1 and minus 3. It would give us the two numbers in the first column. You can find the size of a matrix using size function. Size of any matrix or any vector would have two numbers. The first number represents the number of rows, and the second one represents the number of columns. So for example, size of A, in this case, this A is going to be 2 and 2. 2 rows, 2 columns. The size of this vector is going to be 1 and 4. The size of B, it's going to be 4 and 1 because it has 4 rows and 1 column. So you can also build matrices from vectors. You can put them beside each other, or you can put them under each other. So here, like, we have a 3 by 1 matrix, or we can think of this as a column vector, 3, 2, 1, 3, 2, 1. And this one has the same size. It's also 3 by 1, 4, minus 6, and 7. If I write A equal to AB, it means that I want to put these two columns beside each other. You can also put a comma here. Use, like, as I mentioned, like for anything that's going to be in the horizontal line in the same row, you can put either a space or comma. So here, like, you see that, like, you put A and B beside each other. We already discussed the difference between matrix operations and element-wise operations in previous videos. So if you want to add or subtract two matrices, you can simply do that. You can just, like, basically add two matrices like this. You just have to make sure that they have the exact same size. However, for multiplication and division, there is a difference between dot asterisk operator and the asterisk operator. Once you have the dot asterisk operator, this means that you want to have element-wise multiplication. It means that in this case, both A and B have to have the same size, and you want to basically multiply the corresponding elements of these two matrices and have the result as element-wise multiplication. If we don't put the dot, this means that we want to have matrix operation. So you're familiar with matrix operation in your previous courses. If you want to have matrix operations, then the number of columns for the first matrix has to be exactly equal to the same to the number of rows for the second matrix. And the matrix multiplication is defined like this. So each element of the result, it's basically a dot product of the corresponding rows and rows of the first matrix and the columns of the second matrix. I'm not going to discuss more because you've already seen this before. A square matrix is a matrix that has the same number of rows and columns. So this is not a square matrix, but this one is, right? So has the same number of rows and columns. One of the functions that you can use in a square matrix is trace of A. That would give us the sum of the diagonal elements of matrix A. This in many cases can be helpful, but I just want to introduce more functions related to matrices in MATLAB. So here you see that, like, this is a function that you can use for a square matrix to find the summation of all the elements on the main diagonal. So Yeah, this is a square matrix. This is also a square matrix because the number of rows and the number of columns are equal. We have a concept called determinant of a matrix, which is a scalar number. It's just going to be a number, not going to be a matrix. Or you can think of like any number, you can think of it as a 1 by 1 matrix, but like it's going to be a scalar. So you already know how to calculate the determinant of a 2 by 2 matrix. So for a 2 by 2 matrix, determinant is going to be AD minus BC. For a 3 by 3 matrix, it can be calculated in many different ways. You can choose any of the rows or columns as basically the pivot, and if we, for example, choose the first row, then the determinant of this matrix is going to be E times IO minus NL minus H times FO minus NG plus M times FL minus IG. Or you can use any other row and column. You just have to know that based on the indices of the pivot that you choose, the elements of the pivot that you choose, the plus or negative sign might be different. Determinant of this matrix, for example, you could just like you see that like how it can be calculated. It doesn't matter which row or which column you're going to choose, it's going to be exactly the same term, the same expression. Like we use the determinant of matrix in this lecture to basically know if a matrix is invertible or not. So the determinant is an essential property of a matrix, and we'll see that if the determinant of a matrix is equal to 0, it means that that matrix is not invertible. And we also like it, that determinant also provides more information about the matrix that we'll see later. Okay, so that's why it's important for us to know the determinant of a matrix. In MATLAB, you can just use the det function to find the determinant of a matrix, of a square matrix, sorry. Like we're only gonna focus on the determinant of a square matrix. Like it doesn't have that much meaning for non-square matrices for our purpose. An identity matrix is what we call a diagonal matrix. So it's a square matrix, first of all, that it has number 1 on the main diagonal elements. All the elements on the main diagonal are equal to 1, and everything else is equal to 0. This is called an identity matrix. So this is an identity matrix with 2 rows and 2 columns. This is an identity matrix with 3 rows and 3 columns, and this would be an identity matrix with n rows and n columns. All the elements on the main diagonal are 1. The rest of the elements are equal to 0. So by definition, an inverse of a matrix A is defined as a matrix that if you multiply it by A, then an A is a square matrix. If you multiply it by A, you would get the identity matrix. And we call this one an inverse of A. And you just like have to pay attention that A should be square, like first of all, because identity matrix is only like defined for square matrices. And also we have the property, commutative property for this expression. So A times A inverse is equal to A inverse times A, and both of them should be equal to identity matrix. In MATLAB, we can use INV of A to find the inverse of a matrix. But similar to other software packages, you have to have a good understanding of what an inverse of a matrix is, what a determinant is. Sometimes the results that we get from software packages, they doesn't have the accuracy or the precision that we need. So we'll see an example of that later. but you just have to be careful when you use like MATLAB or any other software package. Some properties about excuse me, about inversing a matrix. So if you inverse of A inverse is going to be A. So if you inverse a matrix twice, you would get the original matrix. A inverse inverse is equal to A. Inverse of K times A, it's going to be inverse of A divided by K, where K is a scalar. So Ka inverse is going to be A inverse divided by K. Inverse of A transpose, it's the same as inverse of A transposed. So you can just basically switch these two operations. It doesn't matter if you transpose the matrix first and then get its inverse, or first get its inverse and then transpose it. If determinant of A is not equal to 0, A is invertible, and we know that A multiplied by inverse of A is going to be equal to the identity matrix. So this is a very important statement here. Like, if determinant of A is equal to 0, A is invertible. If it is equal to 0, A is not invertible. And we say that when determinant of A is equal to 0, we call A a singular matrix. Okay, so whenever you hear about singular matrix, you should know that its determinant is equal to 0. We're not going to focus on how to calculate the inverse of a matrix like by hand. So like we mostly rely on software packages to do it. For a 2x2 matrix, is very simple to do that. So it's just going to be 1 over determinant of A. You swap the values on the, you swap the elements on the main diagonal and negate the non-diagonal elements. So it's going to be 1 over AD minus BC times D minus B minus CA. So you can see that here it's very obvious why, if determinant of A is equal to 0, matrix A is not invertible. But because like you see that like here we would have 1 over 0. This is determinant of A. But this concept is a general concept for any size, for any number for n, an n by n matrix, if it has its determinant equal to 0, is not invertible. So a singular matrix is not invertible. So one thing that I already mentioned, that when you use any software package, you have to be very careful. Sometimes when you want to calculate determinant of a matrix, or when you want to find the inverse of a matrix, MATLAB doesn't show you 0. It would just like show you a very small number, something times 10 to the power minus 10 or minus 16 or minus 20 or something like that. Okay, so software packages, because these are digital or numeric mathematical simulation packages, they are not going to be very precise in many cases. So you have to be very cautious when you use them. And I mentioned already that like the inverse of a matrix can be calculated using INV function. So here you just like see as an example that here, let's like look at this one. I'm just gonna use the command window. A is equal to, sorry, let me just like see if I can copy paste this. Apparently, oh, I did it twice. There you go. Let me just like remove the semicolon so that we see it. Oh, I missed the A. Sorry. CLC A equal to, I can do it right. Okay, so if I find the determinant of A, it actually shows 0. So this is like a singular matrix, and later on we're gonna see like how by just looking at this matrix, looking at the first two rows, we can know that the determinant of A is going to be equal to 0. We'll see that later. And if I try to calculate inverse of A, we see that like matrix is singular, so and then like we get like infinity for every element of that matrix. If I just replace the first A1, this is the same as A1 and 1, right? So this is the first number. If I just replace the first number with 7, so I just want to do this so that you know that this is equal to A1, right? So this is the case. If I do that now, hopefully, let's look at the determinant of A. It's not 0, so this matrix should be invertible. And this is the inverse of A. Let's see what A times inverse of A is equal to. It's equal to an identity matrix, and the same thing for inverse of A multiplied by A. Okay, so you see that like they're both equal to the identity matrix. Now we know that MATLAB is based on matrix operations. So if we want to solve a system of linear equations in MATLAB, first we have to write it in matrix format. So we have to basically convert this system of linear equations into a matrix equation. So how can we do that? So you see that here we have two unknowns, x1 and x2. And each of the unknowns in each of the equations has a coefficient. So we can create a matrix of coefficients. So in this case, it would be A1, then A3, then in the second row, A2 and A4, which is going to be multiplied by the vector of unknowns, which is going to be a column vector with x1 in the first row and x2 in the second row. And this is going to be equal to the right hand side vector, which is again a column vector, which is equal to c1 and c2. Okay, so you see that if you know the basics of matrix operations, if we have this, if A is A1, A3, if you multiply it by the vector x1 and x2, you get exactly the same left hand side for the first equation, and the same thing for the second row. Okay, so this is how you can convert a system of linear equation into a matrix equation. A is going to be the matrix of coefficients, x excuse me, x is the vector of unknowns, and c is the vector of right hand side. And this basically shows you how a matrix multiplication works. If A is of size n and n, right? So if A is a square matrix, so basically this means that if the number of equations is equal to the number of unknowns, if that's the case, and also if A is non-singular, what does this mean? It means that if its determinant is not equal to 0, then you can find your unknowns by this operation. If I multiply both sides by A inverse times A, it's going to be the identity matrix, and identity matrix times anything, it's going to be equal to the original vector or matrix. So on the left side would have X, and on the right side you would have A inverse times C. So this basically comes by multiplying A inverse on the from the left side of both left and right side, right? But the condition for that is that we should know that A inverse exists. So for A inverse to exist, A has to be non-singular and also has to be, of course, a square matrix. So if we have this system of equation and if we want to solve it, right? So if we want to find our unknowns, which in this case are x and y, so what we need to do is first to write down the matrix of coefficient. In this case, A, we call it A. So you see that in the first equation we have 3 and minus 2, and in the second equation we have 1 and 4 as the coefficients for our unknowns. And our right hand side vector, column vector, is 5 and 11. So if you just like find inverse of A times C, it would give you the answer for, like, it would give you the values for your unknowns. So x is here going to be 3 and y is going to be 2. Okay, the reason we could do this is because inverse of A exists. Determinant of A is not 0. You would see that here. Determinant of A is going to be 3 times 4, 12, plus 2, 14. So because determinant of A is not equal to 0, A is non-singular, and therefore it is invertible. So we can find the vector of unknowns very simply using this operation. One thing that I wanted to show you here is that in a 2D space, so when you have two unknowns, it's as if you have two-dimensional space, right? So like this is going to be our x, this is going to be our y values, and each of these equation is an equation for a line. So here we would have 3x minus 2y equal to 5. That's like this is this equation, probably, yeah. And this one, 1x plus 4y equal to 11, it should be this one, because this one has a positive slope, as you can see. This one has a negative slope, so this is how I can tell that this is the first one, this is the second one. So the answer for this system of equation with two equations and two unknowns is basically a point that exists on both of them. So it's going to be the cross section of them. So you see that x is going to be at 3 and y it's going to be 2, right? So this is like how you can also graphically see what each equation represent. This is of course easy to do for two-dimensional or three-dimensional problems, but for like more than that, it's not going to be very easy to imagine. But I just wanted to show you that how we can do this using MATLAB. So we want to visually represent this. So first I want to clear, let's say, close all CLC. So clear would clear all the variables that we have in the workspace. Close all would close all the figures that we have open from previous runs of MATLAB code. CLC would clear the command window. Now, first thing we want to do, we want to provide a range for our x values. So I saw that in the picture that I had, like I chose from -5 to 5. Let's do the same. We can actually do from -10 to 10. So like this is how I can do it. So I can say -10 to 10. In order to have higher resolution, I'm just gonna put like a step here. Doesn't matter in this case because it's a line, but I just wanted to show you that you can have so this shows the initial point, this shows the final point, and this is the step that goes like, or the resolution that it just like basically shows like how you can go from -10 to 10. Or another way of doing it is going to be x is equal to len space Let me just like do it like this, put it as a comment, not this. X is equal to len space minus 10 comma 10 and the numbers that you want to have, let's say like 1000. Okay, so then we have to write the line equation for the first equation. So like by changing the format of the equation, I can say like y1 is equal to 3 times x minus 5 divided by 2, or like multiplied by 0.5. This is going to be the first equation, and y2, which is going to be the second equation, it's going to be equal to, let's see what that is. It's going to be 1 over 4, or 0.25, multiplied by 11 minus x. Okay, so like I'm just representing this one. So here y is going to be 3x minus 5 divided by 2, and in this one y is going to be 11 minus x divided by 4. So that's what I have here. I hope I'm right. Yes. Okay, so like let's put a semicolon so that this doesn't get echoed. Now I can just plot it. So just let's have a figure opened, and like I'm just gonna say plot. I'm gonna do very simple plotting here. Let's say like x, y1, and let's do this one with the color red, and this other one with blue. Of course, if I want to put both of them on the same figure, I have to put a hold on statement here. Let's just like add grids to our plot. Let's have an x label x and a y label y, and maybe I can also have a title, select system of two equations, two unknowns. Okay, so let's run this, see if this works. I have many things running in my laptop, so that's why it's very slow, but it is running. So let's see how that works. Come on. There you go. Okay, so like you will see that this is the first line, this is the second line, and this shows the cross section, right? So this is the title, this is the X label, Y label. So one thing that graphical representation can help us visualize is basically seeing if our system of equation has any answer, has any solution or not. So here you see very clearly that we have a solution here at this point, which is close to x equal to 3 and y equal to 2. At this point, these two lines intersect. If we have two parallel lines, it means that we have no solution. If we have two lines on top of each other, we have like infinite number of solutions, right? So this is like a graphical method to find the solutions for a system of linear equations. So this was the case for us. So like if the two lines intersect, like this is like for like a two-dimensional space, like meaning like two equations, two unknowns. If the lines intersect at one point, we have one answer, one solution. There's one point that exists on both lines. If we have parallel lines, it means that our system of equation has no solution. There is no point that exists on both of these lines. If we have two lines on top of each other, so like you will see that these two lines are basically the same thing, right? But if you have two equations that represent lines that are going to be on top of each other, how many solutions do we have? How many points do we have that exist on this line and this line? Infinite, right? So we can have one solution, no solution, infinite solution. In many cases, we might have something like this, that we called our system very ill-conditioned. A system is ill-conditioned. Uh, why is that? Because you will see that it's not very clear where the intersection is. Is it here? Is it here? Is it here? Like, where is it? In many cases, we will have something like this. Um, this can be due to, like, for example, like the determinant of the matrix being very small, and we'll see like different cases of these ill-conditioned systems later, right? But here, like, you have to be very careful when you have an ill-conditioned problem. It's just like you can't rely on the precision of software packages. Like, some might give you this point, some might give you this point, so you have to have a like a better vision of the problem. Now we want to see a system of three equations and three unknowns, and so again we can just like follow the same approach that we did for the system of two equations and two unknowns. So first thing that we have to do is to find the matrix of coefficients. So you see that you have to, like, our vector of unknowns is going to be x, y, and z. So the first coefficient is 1, the coefficient for y is 1, the coefficient for z is 1. Here, like, I have to put everything on one side. So if I do that, then coefficient for x becomes -1, coefficient for y is 1, and the coefficient for z is also 1, right? And in this case, again, I'm going to take everything to the other side. The coefficient for x is 1, coefficient for y is 0, because there's no y in the third equation, and coefficient for z becomes -3. Okay, and now that we took everything to the other side, to the left side, we have to be careful about the right hand side vector. So here we have 120, here we have 0, and here we have 0. The constants on the right side are equal to 0 for the second and the third equation, excuse me. And again, we can find the vector of unknowns, so the values for x, y, and z, by inversing the vector of matrix of coefficient and multiplying it by the vector of the right hand side. So this is how you can find the answer, the solution. Similar to system of 2D equations, you might have different cases. You might have, so each of these equations represent a plane in a three-dimensional space. Right now we have the x axis, y axis, and z axis, right? So each of these equations represent a plane, right? So like here, like for example, this can be the plane that for all the points on this plane, x plus y plus z is equal to 120. Okay. For this one, it's going to be another plane. For this one, it's going to be another plane. Okay, so this is basically what we have. I think like I did it wrong. Like this should be, I think, the third one. Anyways, it doesn't matter. So like each of these equations represent a plane here. So these three planes, they can intersect in one point. In that case, our system of equations has only one solution. There is only one point that exists on all of these three planes. You can have the three equations intersect in a line. In that case, how many points do we have that exist on both, on all P1, P2, and P3 at the same time? we have infinite number of points, right? The similar case can happen if P1 and P2 and P3 are like lie on top of each other, or like two of them lie on top of each other and the other one intersect them. So you can have one solution, you can have infinite solutions, and you can have no solutions. If the three planes are parallel to each other, then there's no point that exists at the same time on all P1, P2, and P3. Okay. So again, I want to show you how to plot something like this using MATLAB. We're going to do it very simple. So let's just go back to MATLAB. Okay, maybe I'll just like change this one. So because now we are using a three-dimensional space, we have to provide a range for, you have to provide a range for both x and y. We can do that using the mesh grid function, and we can give the same range for both x and y, or we can give them separate ranges. I'm just gonna give them the same range. So like I will say like both x and y are gonna go from -100 to 100, and I'm gonna use like a step of 1. So it doesn't really matter. So then we just basically have to find the equations of each plane. So let's see like what the equation for the first plane is. Like z1 is going to be equal to, we want to find z1, z2, z3 in terms of x and y. So z1, it's going to be 120 minus x minus y. z2 is going to be equal to x minus y. And z3 is going to be equal to x divided by 3. Okay, so this is basically the equations for these planes. Z is equal to 120 minus x minus y. Z is equal to x minus y. Z is equal to 1 over 3 divided by x. And then again, I want to figure. So let's just change this. If you want to do a 3D plot, we can use either mesh or surf. I'm just going to use mesh. And let's just like have x comma y comma z1. Okay, hold on, and then mesh x comma y comma z2. We don't need to have another hold on, it would hold everything on. Makes x comma y comma z3. We have grid on, x label x, y label y. Let's add a z label, z, and title system of 3 equations, 3 unknowns. Okay, let me double check everything. It looks okay. Okay, so this is how our system of 3 equations, 3 unknowns would look like. And let's just like find an angle that shows everything clearly. This is not the best angle. Like here, you would see that if you look at it, these two planes intersect in a line, and that line goes through the third plane. So this shows that our system has one solution. Okay, so this is how we can represent a system of linear equations. Let me see if I can just like make this a little bit more. Yeah, so like this is like, if I reduce the resolution, you would see that this looks more similar to what we had in the PowerPoint. So like you see that like each of them is a plane, and you can just like basically rotate the plot using this icon. Anyways, so this is how you can visualize your system of linear equations. Of course, this is going to be like mostly useful for like two equations, two unknowns, three equations, three unknowns, or like when you have only two unknowns or three unknowns for things, for like for systems like with more unknowns than three. Then it's hard to visualize them for us because our brain can only digest like 3D at max. This basically shows like the same thing that we did, doing it a little bit differently here, but like this is like providing the range for x and y using linear space, finding the equations for the three lines. You can use either mesh or surf L. You can change the coloring using the color map if you want. That just like makes it like a little bit um, like more visually pleasing, but I just like here, like if you want to like show it in gray, you can do it like with the color map of gray, but basically this is doing the same thing that we did. um, what if you're facing nonlinear equations? So here all the equations that we have seen so far, they are linear. It means that the power for each of the exponential term, like the power for each of these unknowns is equal to 1, right? And we don't have any nonlinear term. It means that we don't have sine of x, log of x, x squared, x cubed, square root of x. We don't have any nonlinearity. Everything is linear, right? If we have a nonlinear system of equation or nonlinear equation, it's not that easy to solve them accurately using like there's no it's hard to find like a general solution, but like there are numerical methods or optimization methods that can help us to solve them. So the optimization toolbox in MATLAB provides a function called fsolve that basically can uh, help us find the solution for a nonlinear equation. You just basically I say basically a lot, I have to stop that. You have to provide a function handle, and you have to give the initial point because it's going to use a numerical solution. It needs to have an initial point, so one initial guess for your solution, and the fsolve function would solve your equation. Example of that would be something like this, that if we want to find the zero crossing of this function, which is very easy to know, like this is going to be x equal to minus 3. At x equal to minus 3, f of x is going to be 0. But if we want to find the zero crossing of this function, you just have to provide a function handle. Like here, this is a function handle. We just say that f2 or f, whatever you want to name it, is going to be a function of x at sign x, x plus 3. That's basically, again, that's the term that we have that we want to find the zero crossing. This is our function, and then we just like say that we want to solve this numerically. This is the function handle, and this is our initial guess. It doesn't have to be very accurate, so we say that like we think that this line, it's gonna cross the x-axis at somewhere close to 0, right? It doesn't have to be very accurate, and the fsolve would give us the exact solution, or not the exact solution, but the numerical solution using an optimization technique. Unfortunately, I don't have the optimization toolbox installed in my MATLAB version, so I can't show it to you. But if you have it installed, then you can try the fsolve function for nonlinear equations. Similar to this, So first of all, is this a linear equation or a nonlinear equation? This part is linear, this part is linear, this is not linear because you have a sign of x. The coefficient for x is not a constant, right? So this is this is causing the nonlinearity. Similar to this one, this is a system of nonlinear equations. This part is linear, this part is linear, but this is a nonlinear term. This is also a nonlinear term. If you want to use fsolve to solve this equation, to find like at what x f of x is going to be equal to 0, you provide the function handle. You write the function, right, and then provide the function handle and an initial guess. We don't have to be very accurate. We just like say that we think that at x equal to 0 this is going to be 0, which obviously is not the case. At x equal to 0 this function is going to be 0.3, but it doesn't have to be very accurate, and then it would find it for us. The problem is going to happen if your function has multiple zero crossings, right? If you provide the wrong initial guess, instead of finding the zero crossing that you are interested in, you might find the other one. Okay. Similarly here, if you want to find a solution for this system of linear equation, nonlinear equations, we provide a function handle. Right here, we have two unknowns, so we can represent them as a vector of unknowns called x, and here x1 would be our x and x2 would be our y. Okay, you can call them whatever you want, but this is how I did it. So this is going to be the first equation, and this is going to be the second equation. So we basically want to know at what value of x and y both of these terms become equal to 0, right? And we have to provide an initial guess for the solution, and we just said that, oh, we think that at x equal to -5 and y equal to -5 both of these are going to be 0, which again, like, obviously is not the case, but using fsolve, once you solve this using MATLAB, it would give you the solution for it based on the optimization method that's used by MATLAB. We're not going to focus on nonlinear equations, so don't worry about it. This is only for your information. You can also use fsolve to solve linear equations though, right? It's not limited to only nonlinear equations. You can use it to solve linear equations as well. So let's just take a break at this point, and then I'm going to continue later.